continuing the topic of climate overview with variations in the climate caused by seasons, so seasonal variation, plus occasional variations by El Nino. We're looking at short-term climate variations. The largest short-term climate variation is the seasonal pictures. And then the next most important short-term climate variation is El Nino and La Nina. Teleconnections, El Nino and La Nina are teleconnections, and there are additional ones that also cause variation in our climate. And shorter term and longer term effects, and we'll mention a few of those. There are many, and so we won't be able to cover all of them. This diagram represents El Nino. So let's start off with seasons. The angle of incidence of sunlight influences radiation received at the Earth's surface. We see here an image of the Earth, possibly on the summer solstice for the northern hemisphere. So we have the sun's rays coming in more directly overhead at the Tropic of Cancer, which occurs right in there. And because the sun is directly overhead, it's more intense. Notice that this beam of sunlight is spreading over a smaller amount of area than this beam of sunlight. This beam of sunlight is the same width as this other one. They're both the same width, but this one's spread out over a larger area. And that causes the sunlight to be less intense at higher latitudes. At lower latitudes, where the sun is directly overhead, that's the most intense. The second effect is the thickness of the atmosphere. So sunlight is more concentrated at the equator, especially right on the first day of spring and the first day of fall when the axis is not tilted, or it's most concentrated at wherever it's straight, the sun is straight overhead, and sunlight is more spread out at the poles. Also at the poles, sunlight is passing through more atmosphere, and that attenuates the sunlight or causes it to diminish a little bit. Notice how thick the atmosphere is. This is very exaggerated, but notice the thickness that the sunlight of atmosphere that the sunlight is passing through here, whereas here it's passing through a larger amount. You can think of a sunset. At sunset, the sun is a lot dimmer. In fact, during the peak of the day, you cannot look at the sun. Do not look at the sun. It will harm your eyes. But at sunset, sometimes you can look at the sun because the sunlight is passing through more atmosphere, and that's making it dimmer. So when the sun is more directly overhead, more energy reaches the surface, the sun is brighter and warmer, more warming is happening. Now, seasons are caused by this tilt of Earth's axis. So if it were not tilted, this axis would be straight up and down with respect to the sun's rays, or as measured compared to the plane of Earth's orbit around the sun. But the Earth's axis is tilted, and on the first day of summer in the northern hemisphere, the axis is most tilted towards the sun, and that is June 21st, approximately. This picture is for spring and summer in the northern hemisphere, so it could be before the solstice or after the summer solstice, either spring or summer, and it's fall and winter for the southern hemisphere, so it could be before or after the winter solstice. That's the same day. The winter solstice in the southern hemisphere is June 21st. Now next I want to show you a little activity, next I want to show you Earth's orbit and its behavior as it goes around the sun. So we're drawing an ellipse to represent Earth's orbit around the sun. This is the ellipse that we made, and you see two focuses, or foci. Here's one, and here's another one. That's where we had the pencils in place to allow the string to go around to make the ellipse. And if this represents Earth's orbit here around the sun would be at one of these foci. Here is the sun, and the Earth sits here on the orbit. That's the orbit going around that ellipse. And the Earth's axis is most tilted towards the sun at a time when the Earth is pretty far away from the sun. Its farthest is July 4th, but here on June 21st, this is the summer solstice, and the Earth's axis is tilted towards the sun, and we have summer solstice for the northern hemisphere, winter solstice for the southern hemisphere. Now, as the Earth goes around the sun, the axis continues to point in the same direction in space, so that on December 21st, the axis is pointing away from the sun, and that happens to coincide with, or almost closest to the sun. The closest to the sun would be here at perihelion, and that is January 3rd. When the Earth goes around the sun, the tilt of the axis creates the seasons. When our axis is pointing away from the sun, we get less sunshine. The sunshine's more spread out, and it has to pass through more atmosphere. And when the axis is pointed more towards the sun for our hemisphere, then we get more sunlight. That is the warming season. So we're warming from around here all the way around here. We're warming, and then it starts to cool off. So we've got warming seasons of spring and summer till pretty late in the summer, and then it starts to cool off. Fall is cooling, and a lot of winter is still cooling, although it starts to warm up again. Here we see January temperatures surround the Earth, and you can see in January, which is winter in the northern hemisphere, it's a lot warmer in the southern hemisphere. And then if you look at July temperatures, we see that warmer temperatures have moved into the northern hemisphere, and they're pretty much centered around the Tropic of Cancer. This wind map for January shows you that the higher wind speeds in the winter are occurring way far north, whereas if we see a similar map for July, we see the higher wind speeds are in the south. So higher wind speeds tend to be during the winter. This link shows us the temperature changes through the seasons. Let's go ahead and check out that link. So here we see the temperatures shifting across the world for different months. So in the summer, for the northern hemisphere, we're seeing a lot warmer temperatures, and then it cools off and shifts farther south. The ITCZ that we talked about before is shifting north and south with this. And also the polar fronts are shifting. So the ITCZ is right here, and now it's shifting farther north, and then it's shifting farther south. And then the polar fronts right in here where the big change in temperatures are occurring. There's another polar front, and they are shifting north and south. And the polar fronts are our frontal systems with the cold fronts and warm fronts and the extratropical cyclones. Now this diagram shows you the different positions of the Earth and the Sun. What causes the seasons? It's not the distance from the Sun. It's the tilt of Earth's axis of rotation. Solstices are the longest and shortest days. And the equinoxes are days of equal night and equal day. Equinox means equal night. So day and night are equal at the equinoxes. Each of these, the solstices and the equinoxes, are the starts of the seasons. So here is the fall equinox in the northern hemisphere. Here's the sun, and we're starting with the fall equinox in this picture here, and we progress around. Here's the December equinox, etc. And you see how the seasons progress now. For the northern hemisphere, then we're going to get winter between the winter solstice and the spring equinox. We get spring between the spring equinox and the summer solstice. Summer between the summer solstice and the fall equinox. The same names apply for the southern hemisphere. It's just that they're on different dates. So whenever we have a winter, when we have our winter solstice, they have their summer solstice. When we have our spring equinox, also called the vernal equinox, they have their autumnal equinox, or the fall equinox. When we have our summer solstice, they have their winter solstice. Now, I was born in the southern hemisphere, and we had Christmas. That was summer down there, and our candles would kind of droop and because it was so hot. So here is a diagram showing you a particular season. What season is beginning in this picture? This is the beginning of summer in the northern hemisphere and winter in the southern hemisphere. How do we know? We know this because the sun is directly overhead at the Tropic of Cancer. There's the Tropic of Cancer. And because the shadow of the Earth, the difference between day and night, is occurring right at the Arctic Circle. And this one, what season is this? Now I want you to notice that the shadow between day and night is now not right at the Arctic Circle, and so it's not at a solstice. This is either fall or winter. We can't tell which from the picture, or and that's in the northern hemisphere, and spring or summer in the southern hemisphere. How do you know? Because the sun is directly overhead within the southern hemisphere. Okay, within the southern hemisphere, it's directly overhead, not right at the Tropic of Capricorn, and the sun is shining above the Arctic Circle, so it's not the shortest day of the year in the northern hemisphere. So this gives you some of the labels for those different tropics and circles. So we have the Arctic Circle, the Tropic of Cancer, Equator, Tropic of Capricorn, Antarctic Circle. The Tropic of Cancer is at 23.5 degrees north. Tropic of Capricorn is at 23.5 degrees south. It's approximately a half, not exactly. And there you see that's the tilt of Earth's axis of rotation. Can you fill out this diagram with the different dates? You might want to try that on your own. I'll give you the answers by just clicking through it, or at least some of the answers. But you might try it without looking. So here's June 21st is summer solstice in the northern hemisphere, which makes it winter solstice in the southern hemisphere. Then we have December 21st over here, which is our winter solstice and the summer solstice in the southern hemisphere. March 21st, first day of spring, the vernal equinox, autumnal equinox in the southern hemisphere. February is about midway between the winter solstice and the vernal equinox in the northern hemisphere. That's the midwinter. Groundhog Day, February 2nd, is approximately the middle of winter, which is why it's celebrated. Winter and summer in the southern hemisphere. Now, distance from the sun is a slight modifier of the seasons. Okay, Earth's orbit is an ellipse, as we said. Notice these numbers here. There's the sun, 152 million kilometers here, 147 million kilometers. There's different distances from the sun. Notice we're closer to the sun in the winter, January 3rd, or plus or minus a day. In the winter, we're closest to the sun for the northern hemisphere winter. And for the northern hemisphere summer, we are farthest from the sun. That modifies our seasons. Notice that you might think that we ought to be warmer when we're closest to the sun. And it's true, we are a little bit warmer, but it's still our winter because our axis is pointed away from the sun. The axis is the important thing for determining winter and summer. But this modifies our winter, so our winter is a little bit warmer in the northern hemisphere because we are a little bit closer to the sun. Notice that when you draw the Earth's orbit accurately, it's hard to see that it's not just a circle. Okay, so the distance from the sun is a slight modifier, and it's much less important than tilt for determining seasonal variation.